So there's a question that came up on Friday about, is it possible to know which of your models is a better model to use without looking at test data? And so my answer to this had been cross-validation. Look at a test set and see which one performs better. And my reasoning was, in practice, that's much easier to do than to use some of these other techniques. But I thought about it over the weekend and decided that it was worth going into a little bit some of the issues related to model selection when you're just looking at performance of different models that you train on your data, and you would like to be able to have some signature of which model is a better one to use. So I want to take a little bit of a digression before going into neural networks on these issues. And normally I don't like to put equations on slides when teaching, but I decided to do this to signal to you that I'm not deriving these things. I just want to give you the flavor of the idea. And there's a lot of literature on this. There's a lot of debates and discussions. So I just want you to get a sense of why it's complicated. Yeah.
Maybe are you going to provide what those citations are for everybody?
I will on the next slide. This one I actually was not going to. The citation for this is Wikipedia. I actually pulled these equations off of Wikipedia. The paper, I forget the author, but it's Wikipedia citation. So the idea with Bayesian model selection is you have a bunch of different candidate models, and you want to know which one is more likely to be the true model given the data that you have. And so let's say you have a simple model, going back to the first day, a line, and a complicated model, which is a 10th order polynomial. You might imagine that you have a prior that simpler models are better. So you might have a prior on your distribution of models and say, I think the simpler one is better. But that would be putting in by hand the idea that simpler, all things being equal, tends to be better. So what you can actually discover from doing this simple Bayesian analysis is that you can actually have a uniform prior on your models. You have no preference for simpler or complex or whatever, and you just look at this posterior of the distribution of models given your data using Bayes' rule, and then what you can do is you can look at your so I didn't define this quantity before, but what you can do is for a given model, you start with some prior on the parameters given the model, and then you combine that with your likelihood, and then you get a posterior distribution, like we said. And in Bayesian inference, instead of picking one value of the parameters to use, you would like to be able to integrate over all the parameters. So you integrate out all the parameters, and that gives you the distribution of the data given your model in general. So this is averaging over all the different parameter combinations. And that's what this quantity here is. Then if you want to make some simple analytic progress, you can approximate this by a Gaussian, which will tend to be a good approximation when you have a large number of data points. And you end up with some best fit values of your parameters. You have a curvature matrix. And what you find in the end is the part that really dominates when you have large numbers of samples is this bit out front here. So what you find is that as the number of parameters gets large, it sort of deprecates the probability of your data given the model, because your model is kind of spreading its predictive power over many different data sets. And if you then put that back in here, what you find is that you shouldn't just look, say you take the log of this, you shouldn't just look at how well your model predicts the data, which is what L here, the likelihood is. But you actually need to penalize it by the number of parameters times the log of the number of data points. Does this make a little bit of sense? So I'm saying I don't actually want to do the calculation. I mainly want to just give you the flavor that what you're trying to do when you do this sort of Bayesian model selection is you want to figure out which of your models is more likely to be true given the data. And it turns out that by integrating out the parameters of your posterior distribution, you get the sort of natural emergence of a preference for simplicity. Yeah?
How do you choose the function form of the prior?
So in the prior on the parameters or the prior on the models?
On the model.
So often you would just keep this to be uniforms, and this actually doesn't affect anything. So this penalty here is sort of an asymptotic result that doesn't depend on these numbers as long as they're all non-zero.
But if you choose a uniform distribution, the prior is not parameter independent.
So in this distribution, there are no parameters. These are the parameters of the model. Yeah, we can talk later. Yeah, you could use a Jeffreys prior or something like that if you wanted this to be reparameterization invariant. Okay, so let me say that one more time. When you do Bayesian model selection, you're trying to figure out which model is more likely to be true once you've seen the data. That seems like a reasonable thing to do. There's another perspective which is different, which says which model makes better predictions on the test data. And one of the reasons I wanted to emphasize these differences is on the first day we talked about how in machine learning, if you work at Spotify or whatever, your goal is to make recommendations to people for what songs they would like or something. And if you can do a good job at making those predictions, you're happy. You don't care whether you found the true model of the person's preferences. Whereas if you're doing science, maybe you want to find something about the truth in your data. So these are very different perspectives in some sense. So the other perspective, which goes under the name Aikiki information criteria or Takeuchi information criteria, is which model makes better predictions. And so the TIC is actually a generalization that is just better than AIC. It's little known because the paper is in Japanese. And so I wasn't able to read the paper. But it's been rediscovered many times. There's a nice paper by Amari, which I usually find very hard to understand, but this paper is very clear. And he calls it the network information criterion. And I'm not going to derive this for you again, but I just want to give you a flavor of what it says. The idea is, let's say you have a true distribution of data in the world. That's your system that you want to model. You get samples from that distribution. That's what the empirical data distribution is. That's Q star. What you would like is to have your closeness to the true distribution be you want to be as close to the true distribution as possible. So if you imagine some measure of discrepancy between distributions, that could be squared error, it could be log whatever. You can show that the true discrepancy between the true distribution and your model after you fit it is equal to the discrepancy on the empirical data plus a term. So T here is actually the number of samples, not N anymore. Plus a term that's 1 over n times the trace of the product of two matrices. Q is the Hessian matrix, and G is the covariance of the gradients. And it turns out there's actually a term that is order 1 here in T. So these results only apply in a particular situation. So this order 1 term turns out to be the same when you consider a nested model family. So polynomials of order 3, order 5, and so on. So you can ignore it in this situation. People often forget that, actually. But so this term now plays the role of what we saw on the last slide, penalizing the number of parameters. So in particular, if you have a situation where the Hessian and the covariance of the gradients are equal, those matrices are equal, this is just the identity, and it's an identity matrix that's the size of the number of parameters. So this just counts the number of parameters for you. When those are not the same, which is generally the case when your model doesn't fit exactly, then this gives you a different kind of structure. Okay, so I mainly want to emphasize this this difference between what you're trying to do here, which is find a model which makes the best predictions on new data, which is quantified by this term on the left, and in the BIC, where you try to find which model is more likely to be the true model given the data. So, are there questions about
Maybe
this
not,
distinction?
not more likely to be the true model, but just more likely given the data.
More likely given the data, yeah.
So in which sense is this model selection? I mean, this is a question of, it's not even choosing the model. This is a question of which models perform better according to some criteria, but it's not how legal it is in some sense, how kosher it is to use it as a model selection criteria.
Right. So first of all, how would you use this as a model selection criteria? You don't know this thing on the left-hand side. You only know these quantities on the right-hand side. Although actually, these matrices in principle are computed over with respect to the true distribution anyway. So you have to get some empirical estimates of these as well. It's another issue. But what you would do for model selection is you would have different models. You would compute this right-hand side, and whichever one is smaller, you would choose that one, right? And then the question is when is that kosher? There are a number of problems with this. One is that both of these are asymptotic results. So this is an expansion in a large number of samples, and on the last slide with the BIC, you do a Laplace approximation, which is again sort of a large number of samples approximation. So when you don't have large number of samples, you have to worry about that. And how do you know if you have large enough samples? This is an issue. Another problem is that at least, and this is especially a problem in sort of modern, big, over-parameterized neural networks. All of these matrices, in particular things like the Hessian, have a huge sea of essentially zero eigenvalues. So you can't, first of all, you can't compute it when you have 100 million parameters, and second of all, you can't compute the inverse because it's not well defined. So all these techniques have serious issues when trying to actually apply them, and that was one of the reasons why I said you should use cross-validation. But I think it's important to recognize the distinction between these two approaches, between trying to find the model that's more likely and the model that makes better predictions. And in some sense, it's kind of surprising that those aren't necessarily the same thing. Yeah.
So if you had a large number of samples and you compared models versus cross-validation versus this model selection, would they agree?
Sorry, say it again. You're saying if I just do have a large number of samples and I test this, how well does it perform?
Yeah.
So I'll actually show you.
Compared to cross-validation, I guess.
Yeah, I won't show you that, but I'll show you. So, in some sense, this is sort of like your training error, and this is your testing error, and the difference between those is called the generalization gap. So I'll show you some experiments on the next slide for how well this quantity in particular correlates with generalization gap.
I think it's a more fundamental sort of question that has been asked, right? What is asymptotic? Can we say what is the asymptotic result of, let's say, cross-validation? Does it map into?
Oh, that maps into AIC.
Or
that
which one of them?
that maps into this AIC-like framework. Yeah. Yeah, exactly.
So then cross-validation maximizes predictive error, right?
Right.
It doesn't choose the most likely model.
Not necessarily. Right. Okay. So this is a little bit subtle. That's why I thought it was worth going into. So if you want to actually apply this on a big model with a lot of parameters, it's going to tend to be kind of sloppy and have a lot of parameter directions that are sort of poorly constrained, so you can't actually perform this inverse of this Hessian matrix. So there's a paper from
Sorry, you started, and then we interrupted you, right? You started saying that it's maybe not kind of surprising that the two things are not the same. So can you tell us why? That maximizing probability versus minimizing error are not necessarily the same, and how can we make them the same?
I don't have a great answer to that right now. Do you have a perspective on this?
I don't have a great answer either, but I mean, in some sense, I think the big issue is the big difference between all of this is whether you are doing predictions on the future data set in a bulk versus you are allowing yourself to, as you get an extra next data point, you are allowing yourself to sharpen your estimates. Right? So here, when you're doing cross-validation, you are saying that I'm going to minimize an error, which I'm trying to estimate an error on predicting a whole bulk of data, right? The future data that I haven't seen coming in bulk. But in principle, you could have seen, you could have had a situation where I am only trying to predict the next point, and then I'm going to use the next point to re-evaluate my parameters or my models. Right now I have a data set which is n+1 data points. And from that point on, I predict the next one, and then I re-evaluate, and I predict the next one, and then re-evaluate. And so I'm progressively making my predictions finer and finer. And I think in that case, the cross-validation done this way is actually equivalent to not AIC, but rather BIC, right? Asymptotically.
I'm not sure.
I know the result, but I don't know how to make sense of it, right?
Uh-huh. Yeah, that's not obvious to me. Yeah, I don't have too much to say about this. Okay, in some sense, let me study the simpler question, which is how well does this result predict the generalization gap? So there are a bunch of first of all, there's this large number of samples approximation. There's also this subtlety that is not written on here that I said that you can only compare models within a nested class, and they're going to not do that on the next slide. Moreover, you have to deal with these issues of having parameter directions that are poorly constrained, and the Hessian has a bunch of flat directions. So what's done in the following experiments is they cut off the spectrum of the Hessian at some value, and then live within that subspace, invert within that subspace, and look at this quantity, and they see how well that thing correlates with.
These pi is pi tilde and pi star. What are they?
I don't want to worry too much about it. Pi star is the distribution of best parameters given that you're sampling from a true distribution. So it's over samplings of the data, you'll get different best fit possible parameter values on that empirical data, and then this pi tilde is about the learning dynamics and doing sort of SGD, and you get a stationary distribution of parameters. But let me not worry about it. So this is a paper from about a month ago called Information Matrices and Generalization, and unfortunately they don't look at BIC, so I can't show you what happens there. But again, BIC is not meant to predict the generalization gap, whereas TIC is explicitly trying to tell you what that is. And in particular, if we look at the top, you can compute these quantities. They use a different notation. H is the Hessian, C is the covariance of the gradients. You can compute that on the training data or on the testing data. And what they did is they trained a huge number of models. They trained a multi-layer perceptron, a bigger multi-layer perceptron, a convolutional network with something called batch norm, logistic regression, a bunch of things that we haven't even talked about yet. and a bunch of different data sets of images, and then they trained with a bunch of different hyperparameters like learning rates and things that we talked about last time. So a huge number of different modeling situations, and then plotted the difference between training and testing versus this TIC-like quantity. And if you compute the Hessian and the covariance of the gradients on the training data, you get a plot that looks like this. If you compute them on the testing data, you get a plot that's much nicer, and you can see a very clear relationship between this TIC penalty and the generalization gap. So this paper argues that the TIC is actually useful for neural networks. It's worth emphasizing that the models that they train here are extremely small compared with the ones that you would use on at scale with a big data set today. But it's encouraging that this actually seems to predict the generalization gap pretty well. Yeah.
I'm just a little bit confused whether it's a practical point or a fundamental point. So is there a practical point about being able to compute the generalization gap, or is it a fundamental point about what it really means?
I would say practical. So the generalization gap in principle is just the difference between training and testing. And it's certainly possible to have a small generalization gap and perform terribly, right? Training and testing could be equal and terrible, right? So this is just showing that you can actually predict generalization gap from these matrices. Of course, it's a little bit of a less impressive in the sense that if you want to predict generalization gap, you need to evaluate these matrices on the test set. So,
So what's the point? I don't see what you gain. Am I confused?
no, you're not confused. Yeah.
But would this depend largely on the data set that you're training on?
So it's certainly going to depend on the data set, on the model, and so on. Here they did something where they averaged together a bunch of different data sets and models and so on. And if you want to look at what an individual data set does, you have to look at the different shapes of the points. So for, say, street view house numbers, they're the squares, and you can see that they sort of go all around here. Similarly for the x's on MNIST and for CFAR10. If you look at other things like how well does one particular model correlate, then it's somewhat less good. So logistic regression sort of is right here and looks kind of vertical. So this is really something that you see across different models as opposed to necessarily just one. Okay, so maybe this confused you more, and maybe the answer of cross validation is the best way to decide which model is the best is a simpler answer. But I think it's worth knowing about these issues and knowing about these subtleties because they really are kind of fundamental issues when doing machine learning. Okay.
Clarify the difference between the tilde, like empirical, and the like the H tilde and the H. What's the difference between them?
Yeah. So I don't have the equations here, but so H is the same thing as Q here. Sorry. And this is the Hessian matrix of your loss. So you take two derivatives, and then you have to evaluate your loss on a data set, or you have to take an expectation value of this with respect to some distribution. And on the right-hand side is taking that expectation value with respect to the true distribution, which they approximate by doing it on the test set, which is not the data that they trained on. And on the other side, so over here, they compute these expectation values on the test set that they did not train on. Over here, this is on the training set that they trained on. Cool. Yeah.
Let's assume you have some data set
Sorry, I'm having trouble hearing you. Say this again.
So let's say you have a simple model with like two parameters, but the model itself is highly nonlinear. So like all data points are like distributed in almost a paired way. Will we be able to figure that out
In principle, asymptotically, yes, but your point is that not all parameters are created equal. Is that what you're? Yeah. So asymptotically, this you lose that subtlety sort of when you look in this asymptotic limit. I think is the best I can do to answer that. But this does not assume that all parameters are equivalent in some sense. Yeah.
So most of the structure that's nonlinear in the first plot is coming from these CNNs, and I think seems so. Do you have an intuition for that? So if you take that out, it's pretty linear.
Yeah, I don't have a great intuition for this. Yeah, I haven't fully digested this. Some of these results. There are a bunch of other subtleties that we could talk about that get us too far afield as well. Okay. So my plan is to move on and talk about neural networks. So are there any more questions before I do that on these model selection kinds of issues? Okay. So last time we ended by talking about logistic regression, and neural networks are related to models that look like logistic regression through a couple of different perspectives. The first one is you can think about a logistic regression model as having a bunch of different input dimensions coming in, multiplying them by some parameters, adding up to sum, adding a bias, and then passing that quantity through this nonlinear transformation, right? And then we make predictions about cats or dogs or whatever we said. And what's done in neural networks is you say, okay, this model of logistic regression is too simple, and I'd like to make it more complicated so it can do more things. And what you do is you take a bunch of those models, and rather than having them just predict the output of cats or dogs, they send their output to another logistic regressor where the input now becomes the output of some neurons at a previous stage. And then you do this in a stepwise sense. So you have a bunch working in parallel. They do all their computation. They send that all to an X layer. They all do the computation and so on until you get to the output. So that's one perspective on the relationship between these things. Another perspective is imagine just this output layer being our logistic regression model. There was nothing about logistic regression that told us that what goes in here, the x's that go in here, had to be like microscopic data, like pixels or neurons or whatever we're trying to model. They could be transformations of the input, and or what you might call features of the input. And what you could do then is instead of sending just x's in, you could send phi of x, some transformation of x in, and then do a logistic regression model. But then you have to know what kind of transformation should I do. And for a long time, what people did was they thought hard about what kinds of features are useful in the data. So Leo last time said, well, the pictures of I think I have them here. The pictures of the cats and the dogs, the cats have ears that stick up and the dogs have floppy ears. So why don't I just make a feature that can tell whether ears are sticking up or not, and then I can just train a logistic regressor on features like that. And you could do that, but that requires a lot of expert knowledge. And oftentimes you have some new data that you don't really understand. And even when you do have expert knowledge, it turns out that in many cases, what you can do instead of assuming those features or designing them, you can learn them directly from the data. And you can think of what most of the neural network is doing, is creating a transformation that allows you a representation at this top layer, which then a simple logistic regression type model can classify the data simply. Does that make some intuitive sense? So the connection between these little units being like logistic regression is limited to the case where the nonlinearity that you pass this object through is this sigmoid here, and there are many different choices for what kind of nonlinearity you could use, and at that point the precise relationship is lost to some extent, and in fact the type of nonlinearity that is most common these days is this one on the bottom left here called a ReLU, or rectified linear unit, which is almost linear. It just says do nothing if you're below some threshold, and then if this crosses some threshold, just return it. Exactly. Okay. So there was something I wanted to emphasize before I actually told you this, which is I wanted to tell you. Oh yeah, go ahead.
I guess super basic question. How do you build the initial input layer? Let's say you have a set of inputs that are basically a set of 8-bit numbers. Then how do you build the layer that maybe like binary or binary?
Sorry, you're asking how would I encode the data? It really depends on what kind of data you have. There's some representations that are going to be better or worse, but that gets a little bit involved. So maybe I can defer that for a little bit.
But does it mean that, let's say you have like 100 pixels in each 8-bit communication? So do you have to have enough nodes in your input layer to have the same number? Or can you
In the simplest situation, the number of inputs is the number of, say, pixels in your image. Yeah. Or if they're grayscale, if they're 3-channel color, then you have, yeah. Yeah, was that what you were asking?
No, it was just more like technical question. It was like sometimes it looks like black box you need, and sometimes it looks out.
How this process actually works? So I'll write that down in a minute. Yeah.
Maybe it's a longer question. But do you have any intuition for why? So the ReLU in this case is a special case of the leaky ReLU and the exponential linear unit, right? But why does ReLU work so well for so many models and data sets, whereas the other ones where you relax this constraint actually work worse?
You're asking about ReLU versus the others on the bottom?
Yeah.
So I'm actually not an expert in these kind of architectural design choices. So I actually don't know. Is it the case that they work better than these?
In practice, people find ReLUs to be much more successful, and I don't know why.
It's actually kind of meaningful in some sense, right? So if your variables that you are dealing with are positive definite variables, then ReLUs are good, right? If your variables are limited between 0 and x, whatever that x is, right? So your the actual variable that you are measuring from, then ReLUs are not good, and you probably want to use some kind of sigmoidal functions. It's sort of the usual things that we as physicists do: enumerate symmetries, enumerate constraints on variables, and see what matches. Right? It's not useful to put a binary variable in a case where the variable that you are dealing with is really real values, right? It's going to truncate the edges, right? And the other way around. And so if you are dealing with just binary images, 0, 1, right, black and white, then sigmoidals actually work quite well. Everything's fine, right? But if you're dealing with real valued 0 to 156 colored image, then at that point you might as well already use something that is more or less continuous, right? Or unlimited.
So what's the distinction between like your these positive definite and being limited between 0 and x?
Positive definite is between 0 and infinity,
Okay.
more or less, right? That
So bounded versus unbounded?
bounded and bounded, right? And all of these choices are meaningful.
Yeah, in principle, there's a fairly large, effort for architecture design and evolving both the sort of structure of the nonlinearities and the kinds of connectivities and so on that you want for particular kinds of problems. That is more than I can get into here, let's say. But I want to emphasize that there's sort of four categories of neural networks, and I'm only going to talk about one of them today. And I'll talk about another one of them tomorrow. So the first is general purpose neural nets. And the reason I call it general purpose is I want to contrast that with neural networks explicitly designed for things like images. So that's convolutional neural networks. And so in general, if you know something about your data, like Ilya was saying before, that can inform the type, the kinds of decisions you make in terms of, say, the nonlinearities or aspects of the architecture. And the neural networks that make the news these days, mainly over the past number of years, have been something called convolutional neural networks, where let's say you go back to these images of cats and dogs. If you have a dog in an image, in this case they're nicely sort of centered and circled, but the dog could be anywhere in principle, and you would like to have features that can detect a dog anywhere. So you, if you know that about your data, there are two things that you could do. You could take every sample of your data, and you could make more data by moving it around, by shifting it and rotating it and scaling it with all sorts of invariances that you want to have your model build in. But then these parameters have to do a lot of work to figure out that there are all those invariances. And a better thing to do is to just build them in by hand into the architecture. And that's what convolutional neural networks do. So when I say general purpose neural networks, I really just mean neural networks that essentially look like this, where there was no additional architectural constraint that builds in some invariance like translational invariance that is inherent to convolutional networks. Does that make sense? Yeah.
Besides translational invariance, is there another invariance that can be done using convolutional networks?
Using convolutional networks. There's a field called geometric deep learning, where people try to generalize this to a broader class of symmetries. But I'm going to put that, so not for images in particular, but for when you have a general set of symmetries that you would like to encode. It's an active area of research right now. A third type, which has a similar flavor, in a sense, are called recurrent neural networks. And these are neural networks where you imagine that you just have a population of these neurons, and there are no layers in the neural network itself. The layers correspond to time steps, so the neurons just talk to themselves in time. In that case, the number of neurons in each layer is staying constant, right? Because we're not killing off neurons. And then the connections at each stage stay the same as well. So you tie the parameters together. And that tying of the parameters together is another kind of design choice, like translational symmetry. Now you're assuming sort of temporal symmetry. Yeah.
Speaking between about difference between 1 and 2, right? Do we actually need to design special purpose networks rather than just take our data set and apply all certain transformations that we want the network to preserve and basically make a huge data set out of it? Like take every image and translate it left, right by all amounts. I start with billion, I will have 1 trillion images, and then train on that, and I would hope that the network will recover, right, the appropriate symmetries if the data is actually symmetric.
Yeah.
Why is that not the right way of doing it?
It is something that people do, and in particular used to do more. It's just very computationally expensive, right? And if you if you know that you want a certain kind of symmetry, it's much cheaper to figure out how to just build it into the architecture of the network. Because even if you have 1 billion to 1 trillion samples now, exact translation, rotation variance, and so on is going to require very precise settings of all of these parameters, and it's going to take a long time to learn that properly. Okay, so there are recurrent neural networks that work for time series, and whenever you have a model that is dynamical in a sense. I should say, so there was a time when, say, around 2012 to 2017, when recurrent neural networks were all the rage for speech and language and so on. And in 2017, there was a paper that came out that introduced something called a transformer, and this has taken off. And now, mostly, if you're doing things on language, you're working with these transformer networks and not recurrent neural networks. So these are now out of fashion to a large extent. So I'm not going to talk about them here. You look upset.
Please tell me what a transformer is.
I'm not planning on talking about it. It's a cartoon.
Is it one of these categories, or is it turn time into a convolutional method?
A little bit like that.
Yeah.
It in particular focuses on something called attention, which allows you to build in very long-range temporal dependencies. So building in long-range temporal dependencies in recurrent neural networks is difficult, and there are architectures of recurrent neural networks that were designed to build in those dependencies, in particular something called long short-term memory networks, or LSTM networks. And those did a pretty good job, but it still required the model to figure out how to hold on to things. And people started working with something called attention that allowed you to sort of hold on to something and focus on it for a particular time in the future. And then people realized that they could throw away the LSTM part of it and just have a model that was really just attention-based. So the paper is actually called Attention is All You Need. Okay. And I don't know if you have seen these this model called GPT-2 that OpenAI created. That's a language model that is quite impressive. I recommend, so they train it on subreddits, and they have it sort of reproduce, or someone made a small version. They made it reproduce language in various subreddits. And there's one subreddit called Totally Not Robots, which is people pretending to be robots, pretending to be humans. So then they train GPT-2 on it, so it's a robot pretending to be a human, pretending to be a robot, pretending to be a human. It's quite entertaining. Okay. And then the last one is neural networks for unsupervised learning. and we haven't talked about unsupervised learning yet, so I'm going to save this for next lecture. But in general, a neural network like this takes input, which we're calling x, and it produces an output, which we've been calling y. And the data comes in the form of x-y pairs. And your goal is to learn a conditional of p of y given x. And that's a very common task. But you also might want to just have a model that is a representation of the data x itself. Let's say there are no labels. You just have images. You just have patterns of neural network activity. You want a model that reproduces those patterns. So that's generally unsupervised learning. And there are various ways of doing it. And a lot of them are connected in some way to neural networks. So that's what the next lecture will be focused on. Okay. Does this make sense? So this is today. Okay. So someone asked for a less hand-wavy description of what actually goes on here. So if I denote the nonlinearity by sigma, what I mean is that if I think about the activity of some neuron in some layer, then that's going to be say this one. This one is going to take all of the inputs that were coming into it, hit them with some set of parameters w, and then pass it through a nonlinearity. So we're going to take all of the inputs in the previous layer, hit them with a nonlinearity that connects neuron k in the previous layer to this neuron j, and I'll have L up here be the weights at layer leading into L. And then I might have a bias term for that neuron in that layer. And then I pass it through some nonlinearity where this could be a sigmoid, it could be a ReLU, it could be whatever. Yeah?
Can you tell us what the J, L, and these, what do they label?
Yeah, so L is the layer. Let's see. So J is if I draw a diagram, this is neuron J in the Lth layer, and it has a bunch of inputs from other neurons that are neuron K. And this W is going to be the weights into layer L. Sigma is just going to be any choice of one of these nonlinearities. It could be a sigmoid, it could be a ReLU, it could be anything. We'll keep it general.
Is it function?
Yeah, it's one of these functions. And this quantity that goes into the nonlinearity, we're going to call Z. So this defines Z. Does this make sense? So now we just do this. We have, at the first stage, our inputs are actually just the inputs. And then we get our activity is A at layer 1 by running that equation for each of these. Then we get a bunch of A's. We treat those A's now as input into the next layer, and we iterate that, and we get all the way through. Okay? And once we do that, we get to some output layer, which is making a prediction. And that prediction, just like we did for logistic regression or squared error or whatnot, you compare that to a true label. with respect to some measure, and that gives you a measure of performance on that sample. And then you have to do this for each sample. So this is generally called the forward pass. So you iterate this. For the forward pass. And I want to keep things very general, so I don't want to write down an error function. I just want to imagine that you have chosen some error function, whether it's squared error or cross entropy, like we had for logistic regression or whatever. There's some error, okay? So this is what you do if you have parameters b's and w's, but we need to find some way of learning those parameters. And what I said, in the last lectures was just take the gradient of the error with respect to those parameters and do stochastic gradient descent with the learning rate schedule and momentum, and you'll be fine, right? But computing that gradient is actually a little bit difficult, right? There are, many parameters. It's not super obvious how we go about doing that. And there's a very famous method called backpropagation, which these days you don't actually look at because Google's TensorFlow or Facebook's PyTorch or whatever have in them autograd functions where you just keep track of everything that's happening, and then you end up with your error as a function of these parameters implicitly. You tell it to take the gradient, and then you have it in hand. So you can run one line of code and it gets it for you. So usually people don't actually write down the backpropagation equations. I want to do that because I want to make you miserable.
Good.
Good. Yeah. Okay. So I'm going to put them on a different. I should have not written that there. Okay. Oh, I have another one. So let's remember this notation because we're going to need it. So what we're going to do is first think about so we have some cost function, which I'll call E, which depends on the output at the last layer. So that's, say capital L is the number of layers. So you might have some activities, AL sub j. And it explicitly depends on these, because these are making your predictions. But it implicitly depends on the activities of all of the other neurons before it. So what we're going to define is a quantity delta. And it's going to have an index j, and first a capital L, which will just be the derivative of our cost function with respect to the input to neuron j in the last layer. So this is with respect to z, not with respect to a. Okay. And we can also, so I should say define. We should also define a similar quantity in a general layer, which is the error, the derivative of the error with respect to the z in some general layer L. And the inputs to some neuron only affect the error at the end through the outputs of the neuron. So we can use the chain rule here to say that this is equal to the derivative of the error with respect to its outputs. times the derivative of A with respect to Z, which is just sigma prime, right? Okay. So far I haven't done anything interesting. Also notice that Z and B are linearly related. So this is also, if you want, equal to the derivative of the error with respect to B. So B is a parameter, so we're going to want that derivative. Just as an aside. Okay. The main meat of the backpropagation algorithm says I can compute this the error derivative with respect to the Z on the output directly, but I'm going to need all of these deltas at earlier layers as well. So what I want to do is find a sort of recursion relation that tells me what the deltas are at some layer in terms of the ones at the layer ahead of me. So what you do for that, how do I want to say this? So again, this is dE by d ZJL, and at some layer L, what's going on with neuron J can only affect the error based on what all of the neurons in the next layer are doing. So we can write down a chain rule that says let's sum over all the neurons in the next layer and look at dE by d ZJ in layer, or K, in layer L plus 1 times d Z K L plus 1 DZJ. Does this make sense? And then this here you recognize as the delta on the future layer. Now let's keep this. So now we have to worry about how the Z at the next layer is affected by the Z at the current layer. So you can just use the definition of A and run it through. And you find that this is equal to this. Okay, so now if you have all of the deltas here, you can get the deltas at the previous layer, and then you can run it backwards. So this is called the backward pass.
Is that ZL or ZL plus 1?
I think it's L. This one here?
Yeah, because ZL depends on all stuff at L minus 1.
Right. Yeah. This is L. I'll explain in a second. So maybe now's a good time to explain it actually. So what's the logic of what's going on here? What you have to do if you want to be able to compute these deltas in this backwards way, as you point out, is you need to know what these Z's are, right? And the way you know what these Z's are is you first took your sample and you ran it forward. And then you got all the Z's in each layer and you propagated it forward using this forward pass. And then you held on to all that information. And then when you want to do the backward pass, you use it here. Does that make sense? A little bit?
So at the end you have to go backward to the first layer.
That's right. So first you go forward, compute all the A's and Z's for the A for the activations and Z's for the pre-activations. Keep track of those, and then you look at the error. You take the gradient of the error with respect to the output layer, and then you use this iterative thing to propagate it backwards using the Z's that you had before, because this is going to tell you how much changing the Z at some previous layer is going to affect the next Z, based on where you are in this nonlinearity at that current value. Okay. So the last equation. So you need this equation to start. You need this equation because it tells you the derivative with respect to B. You need this equation because it's the recursion relation. And the fourth equation that you need is simple, at least. So we need the derivative with respect to a parameter, W, in layer L. And that's just dE by dZ times dZ by dW. And this is just delta. And this is just the activation of the previous layer. So once you have all of your A's and Z's from going forward, and you have all of your deltas from going backwards, you can compute the derivative with respect to some W parameter using this, and the derivative with respect to a bias parameter using the fact that it's just equal to the delta. And then you can use that as your gradient, and you can use gradient descent, stochastic gradient descent, whatever you want. Okay. So there are a couple of reasons why I wanted to write this out. One reason is I don't like the idea of you running a line of code and not actually knowing what it does. So another reason is maybe I'll take a brief aside here and say that a lot of people are interested in the neuroscience world, the relationship between these kinds of neural networks and neural networks in the brain. And there are various reasons why these seem like they should be doing something very different from what the brain is doing. Nonetheless, there's some interesting experiments showing that there's similarity. So people are thinking a lot about what aspects of what neural networks are doing can the brain do, and what aspects of it can it not do. And this process of doing this backward pass means that if you have a parameter here, there's a connection between two neurons in some layer. If you want to improve it, you need to know essentially all of the W's in front of it, connecting it all the way to the output. And that's what's called a non-local learning rule. So it's hard to imagine how a neuron in the brain with some synapse connecting them would have all of that information about everything that goes on subsequently. So in some sense, this is one of the biggest problems with connecting neural networks to biological neurons. Yeah?
I mean, people used to think the brain was the internet, too.
Right.
So is there something serious behind it, or is it just that it's the most recent technology that vaguely looks like what a brain can do, and so or is there something more to it than that? Should we care?
I'm fairly agnostic. I lean towards your perspective, but
I mean, there are some things like in visual processing.
so yeah. So people say that the architecture of a convolutional neural network was inspired by the architecture of the ventral visual stream and various things, and then you think about it, and the number of bits of information that went from neuroscience into machine learning is in some sense very small, and you can motivate convolutions in a different way that has nothing to do with the brain, right? At the same time, the space of possible models that you could have worked with is very large. So maybe those are very important few bits of information to get us to some useful structure. But I just wanted to mention that this issue of getting an error derivative layer being related to the future layer, which has the future W's, but that one itself had the W's in front of that, and so on, means that that what's going into here is non-local information. Which certainly, if you want to make an artificial neural network that respected certain constraints of biology, you shouldn't have that probably. And there are people that are working on biologically plausible learning. And there are some interesting results. I haven't yet seen a case where, a recent case where adding biological inspiration allowed you for superior performance. Sort of at best case, you're going to handicap yourself and then try to get approximately as good performance as you had before.
I mean, the weights are also positive and negative for each unit.
You don't respect Dale's law, for example. Yeah. Certainly. Okay. So another reason I wanted to write these down is to show you what can go wrong with backpropagation. And understanding that is actually pretty important for understanding a lot of the architectural designs in modern neural networks. So one of the main problems intuitively is that the delta in some layer depends on the deltas in the next layer times the W. And those depend on the W's ahead of them and so on. So there's products of many W's. And you can imagine then that unless your model is in a special location in parameter space, you're going to end up with derivatives. Say you had a network that wasn't 3 layers deep like I had there, but 100 layers deep. You're going to get gradients that are either huge or tiny, right? And that makes it really difficult to train. So I just want to emphasize that and say, let's imagine. So this is pretty artificial, but they're called artificial neural networks, so it's okay. A deep neural network with one layer, one unit per layer, and there's a parameter W, and we have a total of L layers. So then if you use this error derivative, you find that the delta in the first layer, so you want to go all the way back to the first layer, is whatever the error in the last layer was. There's only one neuron. Times this parameter W to the L, times this product of the sigma primes. Okay. And if you imagine that this is roughly constant, so the activation is sort of stationary, then you can see when W times whatever that sigma prime is bigger or less than 1, you're going to get vanishing or exploding gradients. And as a result, you really need to initialize your network very carefully so that you get an error derivative that stays reasonable, right? So there's one of the very important subtleties in training neural networks is to initialize your parameters well, so that you start out with gradients that are reasonable, and then you can keep making progress. And this is supposed to sort of just give you a simple flavor of that. Another aspect is that you end up with the product of all of these sigma primes evaluated at whatever the activity was going forward. And you can see that if you have nonlinearities such that they saturate, so you're over here, then those sigma primes are going to be very small in many cases, and it's going to cut down these derivatives, and you're not going to get very much juice out of it. So that was one of the original motivations of having a nonlinearity that did not saturate on the top end in particular, so that you were able to have a sigma prime that was not vanishing as z got large. You might wonder, whoever asked the question before, then what about on the left side? Maybe you think that the leaky ReLU is better because then the derivative doesn't vanish on either case. And I think that was the intuition. But empirically, apparently it seems like that doesn't help. Okay. Okay. Does this make sense?
So how do you fix the vanishing ReLU?
So the first thing that you do is you find a way of setting initial values of the parameters carefully, so that when you run all this forward, you end up with activations that are not way out on one side or the other, and products that are not huge or small. And in practice, that's beyond the scope of what I can tell you today for actually how to do that. You can find easily on Google all sorts of initialization schemes. But this is one of the really important aspects of training neural networks that can take a long time to get right if you don't know what you're doing. So I recommend Googling. There are a number of other architectural tweaks that are used for various reasons. One of them being related to this issue of vanishing and exploding gradients that I'm not planning on talking about because it starts getting a little bit too engineering flavored. There's something called residual connections or ResNets, where you have connections that just sort of propagate information forward without any change, and that sort of can help with trainability. There's something that you do called batch normalization that again I'm not going to get into, and exactly why it works is a little bit a matter of current research. But these other like bells and whistles that you see do have, in some sense, they're a reflection of some of these difficulties of training and trying to make training easier, as well as other things. Okay. Okay. Any questions about backpropagation in particular? Anything left? So it's tempting to say that that this is just the chain rule. At the same time, it's a little bit more involved. And if you start from scratch, like it seems like it's just the chain rule. It should be easy. Like write this down, and then try to come up with this yourself. It takes a little bit. It's not totally obvious that this structure is the way to do things. And before people had come up with this, there were all sorts of much slower ways of optimizing these models. Yeah.
Why do you have to hold them more?
So you want the gradient of the error with respect to some parameter. And say you're way back here. The only way you can know how changing this parameter affects your performance is to know how changing this parameter affects this and affects this and affects this, and then how that affects this, and so on. So you have to take all that information into account when tweaking this parameter. So you kind of need to start at the end and then use the chain rule backwards. Yeah.
I don't know if you can make this kind of deduction, but is this telling you that you should try and reduce the number of layers in the network as much as possible? Like, is this some sort of, this is what limits the depth of the network, is the fact that your gradient will vanish eventually. So does that mean you should avoid a deep network as much as possible?
So that was certainly the perspective of a number of people 10 years ago, that these things are hard to train for various reasons, this being one of them, another one being that the landscape is maybe glassy. So this is a bad idea. And at the time, what people were trying to do for example, was to say, trying to get a little bit of juice of part 4 here and use it for part 1. So do some sort of unsupervised thing that sets the value of the weights so that you could actually train a deeper network because the weights were initialized in a way that this would actually work well. And eventually, starting around in 2012, people converged on enough, first of all, there's enough computing power, enough data, and then they converged on some of these simple architectural design choices like ReLUs, like initializing the weights, not from a pre-training, but just randomly, but from the right distribution, that allowed you to train a very deep network. Yeah, but certainly people were skeptical until it started working. Another question you can ask, which I wasn't planning on discussing, I'm certainly not going to discuss today because I would need to think about it, is why do you want to have a deep network? So I understand, the argument of I want to do some sort of transformation because logistic regression wasn't enough for me, but what is it about having, 100 layers that's different from having 3 layers? If I have the same number of neurons, why do I want them in many layers as opposed to in wider layers? And there's a lot of activity in this field of expressivity. So I've been focusing on trainability, and there are questions of expressivity and what kind of functions do you compute when you have different kinds of architectural choices.
Is there like something like uniquely sum up that gives intuition for that? Because I've never really heard a satisfying answer. People talk about like multiple scales, but it seems very that is hierarchically ordered in the universe somehow.
Yeah, there are various stories that people tell. So the old thing that people would say is, if your data was generated through some sort of hierarchical process, then you probably should use a hierarchical model to represent it. Maybe that is a better argument for an unsupervised problem, but still has a flavor for the supervised problem. There are simple results showing that if you have these ReLU networks, for example, if you have your input somewhere and you change it just a little bit, the model is actually a linear model, right? As long as you don't pass 0 on any one of the units. And then at some point it becomes nonlinear, and then it's linear for a little while and becomes nonlinear. And you have a number of linear regions. And you can ask how many linear regions can your model produce when you have a shallow network versus a deep network and so on. And people showed that you can have exponentially more linear regions when you have a deep network versus a shallow network. Okay, 2 things. One, you might worry that, am I going to overfit? Is my model so expressive that I can fit anything? And how am I going to generalize in that case? So is more expressivity always better? What you want actually is the right expressivity. You want the model to be able to do the things that the data that you're training it on wants you to do and not other things. And why is it that those things are the right things? So we'll come back to that. Another point, and this is some recent results by a colleague of mine, Boris Heinen, who's a mathematician. He showed that if you initialize these networks randomly, at least, then almost surely you end up with a linear number of regions. So even though you can find precise parameter settings where you have exponential number of regions, you will almost always get just a linear number of regions. So it's actually not the case that the deep networks have that much more expressivity with respect to that measure. So that's why the answer is complicated, and yeah.
So what is the most computationally expensive bit of carrying out this? Is it the computing the sensitivity of the specular, right?
Yeah, it's this backward path.
Couldn't someone imagine like a slightly different architecture where I say I allow every hidden layer to be directly connected also to the input. So I have the inner layers, and then I also have like I jump and I connect to the input directly, and then when I try to cheat, find the sensitivity directly on the output because I'm directly connected to the output, and ignore the ignore my intermediate connections.
Yeah, so this is some of the motivations behind these residual connections, or these ResNets. So you should check those out. And they're, if you're doing something on images, a convolutional network with batch normalization and often residual connections and so on is the choice. So many of the best models use all of these tricks. Okay. I wanted to spend a couple of minutes sort of connecting to the question that you were asking, and try and show you that there's a lot that we really don't understand about neural networks. And I wanted to just give you one experiment from a paper from 2 years ago that is this is not a methods paper. This is just a phenomena paper that has 1,000 citations in 2 years. So it's really gotten people in the theory community interested in trying to understand what's going on. So the idea is if you have a model and you have input data with labels, if I take all those labels and I shuffle them randomly, or I change them however I want, and then I ask the model to fit that those labels, if it can do, if it will say sure I can do that, then the model is in some sense too powerful. So in the framework of sort of standard statistical learning theory, which we touched upon in the beginning of these lectures, the model is so flexible it can do anything you want. So it seems like it should overfit the data when you give it real labels, right? Like how could it possibly generalize to new labels if you can choose any setting of those labels and it will happily absorb those and fit those. So what this paper did is exactly that experiment. And what they did is they took a simple image recognition task and shuffled the labels or not, and they did different things. So the first step is to just take the true labels, which are in blue, and you look at the loss, and it goes down to 0 very quickly, and you fit the training data perfectly. And you can look at the test error, and it does very well. Or it does well enough. And you might think, okay, I'm happy. I have a neural network that I fit my training data, and it generalized to the test set. Then what they did is they randomized the data in various ways. Let me focus on the red curve here, where they randomized the labels, like I was saying. So if you had images of handwritten digits of 0s and 2s and so on, some of the 0s would no longer be labeled 0s. They'd be labeled 6s and 4s and whatever. So I don't mean randomly permuting the labels. I mean randomly shuffling them. So everyone gets a different random label. What you find is that initially the network makes no progress, and you think, okay, phew, it wasn't going to be able to fit that data. But then it comes down, and it takes a lot longer, but eventually it learns to fit that data perfectly. Oh, sorry. This is a learning curve. This is the number. This is steps of learning. Doing gradient descent.
Is it number of samples or number of epochs in the gradient in some?
Related to epochs, yeah. Yeah, the number of gradient steps. And so this is surprising that you have a model that when you trained it on the real data, it got no training error, but then it actually generalized, which I'll show you in a second. But that when you train it on randomly shuffled data, it also memorizes the training data, and it can't possibly generalize in that sense because the test data would also be shuffled, and it would just be random labels as well. So this seems like a big mystery for how is it that these neural networks are so over-parameterized that they're able to fit any setting of the labels that you give them, yet they generalize when you give them the real labels. Yeah?
If you're shuffling according to a distribution, would it be that the network is learning the distribution itself, the shuffling distribution?
So certainly, so you shuffle them so that you preserve the number of classes. So you're not biasing it so there's more classes of one type than the other than in the original data. Is that what you mean?
So for example, if there's a certain probability that a dog gets labeled cat or cat gets labeled dog, then this should be controlled by a distribution, right? A transition probability. So is it possible that it's learning the distribution?
So in this experiment, every cat gets a completely random label of cat or dog. So it's not being permuted with some probability. It's just forget what it originally was labeled as. Just draw it from cat or dog labels, IAD.
So it's uniform.
Yeah. So in that sense, it can't learn. It can't say, I know that I think this is a cat, but I think you're going to shuffle it to a dog or something. It's not doing something like that in this case.
So there's an upper limit to how the network could possibly do. Defined by the distribution.
Yeah, so in this case of randomizing the labels completely, if you have just cats and dogs, then if you give it a test set, it's also going to be randomized, so it's going to be guessing 50-50, and that should be its test error. On the training error, nonetheless, it's able to correctly memorize, whatever that means, all of those labels. Yeah, but they also do an experiment, as you say, where instead of corrupting all of the labels, you corrupt some fraction of them. So if you only corrupt 0.2, then most cats are labeled cats, but some cats are labeled dogs. And you can study the various phenomena that occur when you do that. So in particular on this right graph, as a function of that label corruption fraction, you can look at the test loss, the performance on the test set, going from all true labels. This was not a binary classification. This was 10 classes, so 0.5 is not chance. So 0.9 is chance. So it goes from having good performance for the size. This is a very small neural network. This is a very big neural network. So having good performance to having just chance performance once you randomize all the labels. But in all of these cases, even these simple neural networks are flexible enough that they can fit randomized labels if you give them, if that's all you give them. So this is a one of the sort of galvanizing experimental results of the past 2 years in neural networks for trying to understand the right perspective for why neural networks generalize despite having the capacity to fit any setting of the random labels. Does that make some sense?
But like the word generalization is sort of like, I guess my understanding of it is very vague. I mean, you give it, you ask it to try to predict data that it did not see before that is somewhat similar to the data that it has seen before, and it does well.
Sorry.
But is there like a way to sort of like a mathematical way of?
Yeah, so that's sort of, let's see if we have anything from the. In the context of the first lecture, we're assuming that the test set is drawn from the same distribution as the training set, and then we had all of these statements about what your test error should look like as your complexity changes and so on. And the idea is that the neural network should be so far on this end of things that they have essentially no bias because they can fit anything that you want, but they should have a large variance in this language, and therefore their test performance should be very bad, even though it's data drawn from the same distribution as the training data.
So they are in this yellow circles, like the large yellow circles.
Right. Yeah. So the neural networks are sort of this. Yeah, this one. At least that's the traditional picture. I don't want to say that that's what I think is going. That's why this is a seeming paradox.
So then, what do you think?
we still being recorded?
It's close.
That's probably for discussion, not during a lecture. But you know, it has to be something that's a happy marriage between the structure of the data and the structure in the model. Well, we can talk about this offline. So yeah, maybe we should stop there. Thanks.